The acceleration of a particle depends upon its displacement, like this. So A is minus 4x minus 1 plus x square by 4. Now, given that the velocity of this particle is 17 meter per second when x is 0, you have to find out what is the velocity of this particle when the displacement of this particle is 4 meter. Okay? So basically, you have to find out the relation between velocity and displacement. And we know you can express the acceleration as dv by dt, or there is another form which is v dv by dx. So we are going to use this form to find out the relation between velocity and displacement. So on the left hand side, we will have v dv by dx. And let's open the brackets. On the right hand side, we have 4x minus x cubed. And let's integrate this. V dv, and this is 4x minus x cubed with respect to dx. Right? So on the left hand side, we will have v square by 2. And on the right hand side, we will have 2x square minus x raised to the power 4 by 4. And don't forget about the constant of integration. So to find out the value of v at x is equal to 4 meter, first you have to figure out what is this constant. And that we can do by using this condition, right? So when you put x is equal to 0 in this relation, then you get v as 17. So let's put it here. So this becomes 17 squared, that is 289 divided by 2 is equal to c. So the value of the constant of integration is 289 by 2, and the relation becomes plus 289 by 2. So this is how the velocity of this particle depends upon the displacement of this particle. And now let's quickly put the value x is equal to 4 to find out what's v. So we have v square by 2 on the left hand side. On the right hand side, we have 32 minus, and how much is this? This is 64 plus 289 by 2. So you will get v square by 2 is equal to 225 divided by 2, and the value of v comes out to be 15 meter per second. So as simple as that, we found out in this case the velocity of the particle at x is equal to 4 meter is going to be 15 meter per second. Now in this case, you have a uniform solid sphere which has a mass m and radius r. And this sphere is rolling down the inclined plane which has the angle of inclination theta. The coefficient of limiting friction between the sphere and the inclined plane has been given to you as mu. What do you have to do? You have to find out the maximum value of the angle of inclination theta for which this sphere is going to perform pure rolling. All right? So as the sphere goes down the inclined plane, then the center of this sphere is going to accelerate, right? The velocity of the center of mass is going to increase. And if the pure rolling is happening, if the sphere is rolling without slipping, then the condition for the pure rolling, that is v is equal to r omega and a is equal to r alpha, will be followed. And the angular velocity of this sphere will also keep on increasing as this sphere rolls down. Agreed? And who is going to provide the required torque to this sphere about its axis of rotation? Well, yes. The static friction acting on it up the inclined plane is going to provide that torque. Yes? So what are the different forces acting on it? The static friction force will be acting up the inclined plane, and we can resolve the force of gravity. So mg sine theta would be acting like this, and mg cos theta will be acting perpendicular to the inclined plane like this. And don't forget about the normal reaction. Right? So, in this case, first let's form the equation by using the Newton's second law, assuming that the center of mass is going down with the acceleration a. And don't forget that the mass of this sphere is m and the radius is r. Right? So, we have mg sine theta minus f is equal to ma. This is the first equation. And we will get the second equation by applying tau is equal to I alpha. So about the axis of rotation, let's assume that the angular acceleration of this solid sphere is alpha, right? So we have tau is equal to I alpha. And you can see that about the axis of rotation, the torque of the friction force is Fr. And this is going to be the moment of inertia of the solid sphere, which we know is 2 by 5 mr square. And for the pure rolling, we can write alpha is equal to A by R. So alpha is A by R. From here, you get the value of the static friction force as 2 by 5 ma. Right? Now we can put this value from equation 2 to equation 1. If we do that, then we will get 7 by 5 ma is equal to mg sine theta. Right? So from here, what is going to be the value of 2 by 5 ma? Well, 2 by 5 ma is going to be 2 by 7 mg sine theta. Right? So we get the value of the static friction force as 2 by 7 mg sine theta. And now comes the time of the limiting friction force. We know that the static friction force is going to be less than equal to the limiting friction force, which is mu into n. And as you can see from the free body diagram of this sphere, the normal reaction is equal to mg cos theta. So you have mu mg cos theta. And from here we find out that theta must be less than equal to tan inverse 7 mu by 2, which means that the maximum value of theta is tan inverse 7 mu by 2. So you can take option B in this case as the right option. Now according to this problem, two solid objects x and y have the same volume and they float in a liquid like this. It is observed that x floats with 50% of its volume immersed in liquid and y floats with 25% of its volume above the liquid level. You have to find out the ratio of density of x to y. Now in both the cases, the weight of the object is balanced by the buoyant force, right? And the liquid is the same in both the containers. And we know that according to the Archimedes principle, the buoyant force is equal to the weight of the liquid displaced, right? And you can see that the liquid is displaced more in the case of y. So in the case of y, 75% of the volume is displaced, whereas in the case of x, only 50% of the volume is displaced, and the volume is same, right? So the weight of the liquid displaced is more for y. And you can say that the density of y should be more than the density of the object x. Right? So intuitively, rho x by rho y, this ratio should come out to be less than 1. And from the options, you can see that out of the option B and C, 1 can be right. So from this intuitive thinking, you can discard options A and D. Right? And now let's get mathematical. Let's assume that the volume of both the objects is V. So this is X and this is Y, right? Let's first focus on this object. Let's assume that the density of X is rho X, right? Which means that the force of gravity acting on it is going to be equal to m into g, or you can say rho X into V into g. And this is going to be equal to the buoyant force, and let's assume that the density of the liquid is rho liquid, rho L. So the buoyant force is going to be weight of the liquid displaced, that is rho L V by 2 into G. Right? So we got our first equation. So rho x V into G is going to be equal to rho L V by 2 into G. So this is equation 1. And now let's focus on Y. So assuming that the density of the object Y is rho Y, the weight of this object is going to be rho Y V into G, right? And this will be balanced by the buoyant force acting on it. So you can see the 75% of the volume is immersed inside the liquid for the object Y. So the weight of the liquid displaced is going to be 3 by 4 V into rho of liquid into G. So we have rho Y Vg to be equal to 3 by 4 rho L V into G. Right? And if you perform the operation 1 divided by 2, you will get the required ratio. So rho L will be gone, V and G will be gone, and you have the ratio to be equal to 2:3. So in this case, we can see that option B is the right option. Now let's go through this problem, which is quite interesting. In this case, you have to tell what is going to be the average velocity of molecules of a gas which has a molecular mass m and the temperature is T. Now, one of the assumptions of KTG is that we assume the distribution of the gas molecules to be uniform, right? So this simply means that all the three directions, x, y, and z, all three of them are equivalent and no direction is a preferred direction, right? And that is why the force applied due to the gas molecules because of their bombardment is same on all the 6 walls of the container, right? And that is how the pressure is same everywhere inside the container. So this all is derived when we assume a very simplistic model, and you already know the assumptions of the KTG, right? Those are the assumptions of the model that we work on. So basically you have to find out the average velocity, and do note this is different from average speed. So average velocity will have speed as well as direction. Now if you assume that there are n number of molecules inside this container, then the average velocity is simply going to be the velocity of all the molecules, their summation. So V1 plus V2 plus so on and so forth till Vn divided by n. You know this, right? Now, if a molecule has some velocity v1 at some instant, then you can find another molecule that has the velocity minus v1 at that moment. The probability of this happening is really, really high. And because the number of molecules is so large, you can expect this to happen. And that is why this is going to come out to be 0. Right? Everything is going to get cancelled out. So the average velocity of the molecules will be 0. And you can understand this from a different point of view. Understand this from the center of mass point of view. So the center of mass of the gas molecules is stationary, right? As the container is not going anywhere. And the velocity of the center of mass is actually the average velocity, right? So just to prove that, you can see that the velocity of the center of mass is going to be, and under the assumption we assume the mass of all the molecules to be same. So let's assume that is m. So you know the formula, this is going to be mv1 plus mv2 plus so on and so forth. And let's take m common. So this is going to be v1 plus v2 plus vn divided by the total mass, which is m into number of molecules. And as you can see, this exactly comes out to be equal to V average. And evidently you can see that the center of mass is stationary. It is not moving anywhere, right? So by this logic, you can understand that although the average speed is non-zero, the average velocity of the molecules is 0. And that's how we reach this conclusion. And you can see that option A in this case is going to be the right option. According to this one, a standing wave is maintained in a homogeneous string of cross-sectional area S and density ρ. It is formed by superimposition of two waves traveling in opposite directions given by the equations a sine omega t minus kx and a sine omega t plus kx. You have to find out the total mechanical energy confined between the two adjacent nodes. Now we will find out the total mechanical energy by using the mechanical energy density carried by each wave. So we know that the energy density is given by half rho omega square a square. So this energy density will carried by wave 1 and wave 2, right? So we can tell that the total energy density due to both the waves is going to be 2 times this. And this is going to be rho omega square and amplitude is small a square. So this is the total energy density. But we want the total mechanical energy, right? So we know that the energy density is going to be energy per unit volume, right? And now let's talk about the volume, because once we find the volume into rho omega square a square is going to be our final answer, right? So how much is the volume? Well, between two adjacent nodes, can you see that the distance is lambda by 2, right? So the volume is cross-sectional area S into the distance, which is lambda by 2. But in the options, you cannot see lambda, right? But you see K. So we can express lambda in terms of K. So we know that K is 2 pi by lambda. So lambda becomes 2 pi by K, and this volume becomes S into pi by K. And when we multiply this volume with rho omega square a square, we get rho omega square a square pi s divided by K. And this is the total mechanical energy in this standing wave between the two adjacent nodes, right? So you can take option C as the right option.